So the goal, we have two goals for today. One goal is the main idea of telling the difference between the three tests, the three kinds of chi-squared tests. The chi-squared test of goodness of fit, homogeneity, and the one we're going to learn today, which is the next goal, independence. So here we go. This on page 14, this is your notes. And the first thing, this page, we're going to review what we've already learned. So first, chi-squared goodness of fit. The key to the goodness of fit is that you have claimed percentages for just that one variable. Claimed percentages for that one variable. The degrees of freedom are categories minus 1. And then in your calculator, you use the lists. You do your stat edit list, and you use L1 for your observed, and you do L2 for your expected. All right. Chi-squared test of homogeneity is what we learned yesterday. And that is where you have multiple populations, so multiple groups. In this case, regular peanut and peanut butter M&Ms, but only one category: brown, not brown, milk or not milk. Are you a resident or are you not a resident? So it's just one category that you check amongst these three populations. Okay, so the differences are that we use the matrix in our calculator to run this chi-squared test. Our degrees of freedom are rows minus 1 times columns minus 1. And then this independence is much more involved. This independence condition is much more involved because you have three different populations or three samples that you have to talk about. You have to do, the independence for each one, and say that they are independent of each other. All right, here is today's chi-squared test of independence. So the key here is that you actually have two full and complete variables. For example, here we have one variable, and it's the type of car. And on this other side, we have the variable type of driver. So we have two complete variables, and we're going to see if the two variables are independent of each other, or if they're related, or is there an association between them. Now I will tell you that this first example, because honestly, telling the difference between homogeneity and independence has been very difficult for me, and I've never really totally and completely locked it down until last year, and then I finally got it on paper this year. And the key is that this is just on the homogeneity, one category, but here it was a total variable. So let me explain. If this problem right here with the type of car and the type of driver had been student, not student, then that would have made it a homogeneity problem instead. So again, if this had been student, not student, then that would have changed it to a homogeneity problem. But since this is a variable of multiple things, a student and a different group, the staff, if you had also another one that was administrators or whatever, however many you added on there, that's a whole different variable type of driver. All right, over here we have the classification on the independent, so is the class separate from or independent of the room or the floor that they were assigned to. So the class is a variable and the floor was the other variable. Yes?
Okay, so on the problem yesterday when we had the different types of juices that they drink, like one of them was cranberry, one of them was something else,
Yep.
And then another one was neither. So I get drinking the cranberry and the neither, but I don't get the cranberry and the other one combined because those are two different.
So on the example we had yesterday with the juices, it was a homogeneity because the three groups or the three treatments, the cranberry juice, the lactobacillus, and the neither. What made it the homogeneity is you were seeing if they were getting a UTI or not getting a UTI.
Oh, okay.
So that was your one category, getting a urinary tract infection or not. The three groups were those different drinks.
Okay.
All right. So now, the good thing about this, assumptions and conditions and the calculator computations, exactly the same as yesterday. No difference there. So let's go on to the next page and take a look at this problem. This table shows the rank attained by male and female officers in the New York Police Department. Do this data indicate that men and women are equitably represented at all levels in the department? So you have all your information there. Now, we're going to finish filling out this expected matrix. So you can see 21,900 males are officers. The question is, how many would be expected to be male officers if men and women attained the ranks equitably? So I want to remind you, or tell you if you didn't know, that you don't have to do the totals in the expected matrix. You know, the totals are whatever your totals are. So let's recall, how do you get, what is the formula then for the expected?
Row times column over total total.
Good. The row total times the column total divided by the total. So we're going to take a moment and I'm going to let you fill in those two and we'll check them and see if you get those two correct to make sure you know how to do that.
I peaked in like the first week.
So if you did those correctly, if you did those two formulas correctly, then you got 21,954 male officers and 4,227 female officers are expected. And so that was just filling in those formulas correctly. Now, what are the two variables that this problem is talking about? What are the two?
Gender and rank.
Good. Gender is one of the variables, male and female. And rank is the other one. Very good. Now, let's talk about how to do the null hypothesis and alternative. So I'm going to help you out here with the wording since this is the first time we've done these. So the null hypothesis would be something like this. Gender and rank in the New York Police Department, because we're just talking about that population, not all police departments. And the null hypothesis would be that they are independent of each other. Now, I'm gonna put some other words here that you could also use. That would mean the same thing. Some other options of words. Instead of using the fact that instead of saying they are independent, you could say that they are not related. You could say that they are not affecting each other. You could say that they are not associated with each other. These are different words and phrases that you might see instead of just saying that they are independent of each other. So those things mean the same. All right. So then our alternative hypothesis is going to be that gender and rank in the NYPD are what?
Dependent of each other.
Heck no. Dependent is not a word we're allowed to say in this class because that implies complete dependency. So they are not independent of each other.
You passed the test, Mr. Cole.
Thanks. Okay, and so then let me give you some alternative language for that. Some other words for not independent would be something like they are related, they are affecting each other, and they have an association. They are associated, or they have an association. Okay. So I'm going to say that gender and rank have nothing to do with each other until you prove to me otherwise. That's what this test is going with. So let's check our assumptions and our conditions. And, I was thinking I wasn't going to have to do this, but then first period we started having some questions, and it ended up being that it was a good thing to go ahead and do all of these. So let's then do this. So here's my first thing I want to discuss with you. I have two variables. And last fall, we had this kind of discussion as well. Which of the two variables, gender or rank, is kind of the driving force of this problem? Good. Gender is the one kind of influencing, we're trying to see if gender is influencing rank, not the other way around. Rank does not determine your gender. So when I do my conditions, I will be doing my conditions on those two groups, male and female. All right? I'm not going to do my conditions on officer, detective, captain, higher ranks. So I'm going to assume that the whatever the male and female numbers are, 2653 males, 26,535 males, and 5,109 females are randomly selected. I personally have a problem with that because I'm like, those are such huge numbers. It almost kind of sounds like that's the entire population of the NYPD. So if you don't like saying that they are randomly selected from the NYPD, you could say, I'm going to assume that those are representative of all NYPD employees, officers, or whatever. Yes.
Are we not allowed to say, like, assume randomly selected, or like say such police officers instead of saying the exact number?
Why can't we just say like assume genders are randomly selected?
Assume the male and female officers are randomly selected. Or assume randomly selected
all such
off
officers
are randomly selected. Okay, you can. Yes, you can. I've just kind of gotten in the habit this year of adding that number of officers, but you can just say assume randomly selected male and female officers in the NYPD, and that's okay. All right, next is going to be our independent. So tell me how I have to do this one. Yes, you have two populations that you are checking, so you have to do both of them. That this many are less than 10% of all NYPD males.
Of course there are. So that's like
That means there's
200,000.
65,000 males in the NYPD. Now, I don't know if this is like ever, how many there's going to be ever and in the future, and I don't know. So, but we're going with it. 5109 is less than 10% of all NYPD females. And since I have two groups, I have to do what? Good. These male and female groups are independent of each other.
So we do not have to do all four.
Correct. We're doing our conditions on the male and female groups, not the other four groups. Because male and female is the driving variable. It's the male and female affecting the rank, not the rank telling me if you're male or female.
Is it going to be hard, deciding?
If you can't decide, then pick one of them. I mean, if it's not obvious which one is the driving variable, pick one of them and go with it. I'd pick the one that has the fewest number of groups I'm going to have to do my work on. Okay? All right. Next, let's see. Independent of each other. And then, what do I say last? Large enough is going to be what? All expected counts. And kind of sure I need to reference where those are, or else you would have to list them all. All expected counts, what do I want to say?
Are above 5.
See expected matrix above. Because I do not want to have to list all those out, okay?
Do you have to specify that it's expected?
Yeah, definitely see the expected matrix.
Could you not say see the matrix above?
No, because you have two matrices above. You have an observed matrix and you have an expected matrix.
Both of them are greater than 5.
No. Can you say what? The chart? Sure. Yeah, but you need to label that. Look at the expected numbers, not just one of them. It doesn't matter.
So do we say that every single time, no matter the test, expected
Yes. You always reference the expected numbers. And I conclude with chi-squared model applies. All right. Find the test statistic, the p-value, and note the degrees of freedom. So we got chi-squared, we have our p-value. By the way, what would our degrees of freedom be? Remember that those are rows minus 1 times columns minus 1. Good, because there were 4 rows, 2 columns. And so that degrees of freedom is 3. So I'm going to give you about 2 minutes to put this into your calculator and get the numbers. Go.
Wait, so
If you, after you've put that in your matrix and you got your values, your chi-squared, 70.44, p-value, quite small, 3.44 times 10 to the negative 15, so approximately 0. So let's make a decision. Since our p-value, which is approximately 0, is less than alpha of 0.05, what will we do? We will reject HO. And so now, since we rejected, essentially, since we are rejecting, we have evidence. Let's make our little note. We have evidence of what?
That they aren't
HA
is that
Yeah.
we have evidence of the HA.
Yeah, we have evidence of the HA. So essentially, gender and rank affect each other. If you want to, in our minds, that's kind of what we are saying, is that gender is definitely affecting the rank that is attained. Now, we want more specific information. So let's come over here, and anytime we reject that null hypothesis, we are subject to wanting more information. And we do that with our standardized residuals. So I want to remind you of the formula that goes for standardized residuals is observed minus expected over the square root of expected. And so I want you to do those 2 problems and see if you can't finish completing those 2 numbers and see what you come up with. So do that now. If you calculated that the officer standardized residuals, there's what they are. Now, what I want to talk to you about these numbers, let's have a little discussion. I want you to think of these numbers in terms of a z-score or t-score or, you know, your chi-squared. Or it's kind of think in terms of how many standard deviations you are away from expected. So again, think of these numbers in terms of how many standard deviations the data was above or below what was expected to happen. So this to me would be a very shocking, think in terms of this, in terms of standard deviations. Those females are, look, 6 and 4 standard deviations below what they were expected to achieve.
they are extreme.
So that is pretty extreme. So I'm definitely thinking that the females are quite underrepresented and have much less higher ranks, captain and higher ranks than expected. Okay, so let's make a statement about that. So here we go. Females achieve captain and higher ranks.
Could we say the same for males and captains? Because they're almost 3.
We're going to, but I'm separating it out and saying that females achieve captain and higher ranks much less or lower than, much less than expected. Okay, crazy less than expected. And likewise, the males, see, the males had these numbers that were quite a bit higher than expected. So the males achieve the captain and higher ranks much more than expected. I'm probably not going to put the word much in there just because the females was just insanely a whole bunch less or more, less, I don't know. Captain and higher ranks more than expected. All right, so I probably, you could say some other statements. You could address the officer and detective, but those are not as remarkable.
So you just choose the ones that are like the obvious.
Yes, so I choose the ones that are most remarkable and quite outliers and that kind of stuff. All right, that's how you run a test. Next page. The final objective of today is to see if you can identify the difference between goodness of fit, homogeneity, and independence. So we're going to read a situation, and then we're going to see if you can tell which one of these it is. That's critical. All right, so I'm going to kind of paraphrase these. For time's sake, I'm going to paraphrase what these little situations say. Here we go. This first problem is about a restaurant, and it's talking about the menu and the meals chosen on particular days. It's talking about the meals chosen on Friday, Saturday, and Sunday, and them chosen by or made by chefs A, B, C, or D, 4 different chefs. So envision that this is the way your data is organized. If this is the way your data is organized, what kind of situation do we have going on?
Looks like it's gonna be it's independent.
Independence.
It looks like we have 2 variables, the day and the chef. And so that would mean it's a chi-squared test of independence. The 2 variables ones is the chi-squared test of independence. All right, next problem. This problem talks about 3 different parking lots. There's a parking lot A, which is close to the building. There's a parking lot B, which is a little farther away. And parking lot C is totally across the highway. So we want to see if the rate at which upper management is placed in those lots, because it's supposed to be done randomly, and not upper management. So what would that be?
Homogeneity.
Good. Chi-squared test of homogeneity, because we just have one category, upper management and not upper management,
I thought
across
that's-
those 3 populations.
I thought the not was for goodness of fit.
Nope. So goodness of fit is a claimed percentage for a value.
Like this.
So number 3, we want to know if a student's social life is affected by where the students live. So they ask some categorical. Which category do you fall into? 0, 1 to 2 dates a week, 3 to 4 dates a week,
A week?
or 5 plus? That's what I'm saying. Oh, it says in the past 2 weeks. Sorry.
Still. That's crazy.
All right. And so then,
I'm 5 plus.
listen, we got dormitory, off-campus housing, and living at home. So what we got is this situations here. What type of organization of data do you think we have?
Independence.
Looks like we have 2 variables, and the variables are category of dates, and where you live. So good. Chi-square test of independence. All right, now, one thing we haven't talked about yet, and I was going to also talk to you about it when we go over the homework that we were going to go over. This next problem was intended to not ask you about your dates in terms of a category. See, they placed you in a category. What if they just straight up said, how many dates did you go on in the past week? And people gave answers. And then we would say we took the average. If we took the average for the dorms and the average for the off-campus housing, and we took the average for those that lived at home,
Goodness of fit.
averages are considered quantitative data. This is kind of new. If I had gone over the homework first, I would have already covered this. But averages are quantitative data. Quantities, not categorical. Quantitative, not categorical. That's a problem. That means that you can do no chi-squared test at all, because chi-squared test has to be done with categorical data, not quantitative. So anytime they ask for averages, then you cannot do that, because you would get an average, and that's a no-go. Quantitative. Because when you do things in counts, I have, 20 people that had 0 dates, 20 out of 100. Their counts would be a proportion. Counts would make a proportion. All right, next. We have one group of females. And we're going to be asking these females if they were Democrats, Republicans, or independent. And so I see what they told me. And then I know that they were supposed to be 40%, comparatively speaking, 40% have been Democrats, 40% have been Republicans, and 20% have been independents.
Goodness of fit.
That is the ding, ding, ding. That's the one that gives us claimed percentages. So that's our goodness of fit. Claimed percentages. All right, next. Academic Research Office, we got 3 different majors, courses, humanities, social sciences, or just the sciences. And we want to see how those are distributed across residents and non-residents. So what's that?
Whoa.
Chi-square test, homogeneity, because we just have one category, residences, and we're seeing how those courses are distributed amongst that one category. All right, do you notice this? 45% of this type, 32% this type, 23% that type. Those are the expected percentages. What's it going to be? Goodness of fit. How about this last one? What if the brokerage firm wants to know the average size? Yep. No chi-squared test because that's quantitative.
Sue 'em. How dare they try and come up?
So, you have to do pages 22 and 23 only. You need to skip pages 18 to 20 because we have a quiz tomorrow, so let's make sure we've got down 22 and 23.